Welcome back to machine learning, and today we want to evaluate the performance of logistic regression in face of noise, how it will perform. So we are going to first load or run a model without noise, then we compare that model with noise. So I'm just going to say fit. I'm going to use my data set, which is BC breast cancer data. I'm just going to view it here so that you see the data set that we have. So this is the data set. We have radius, mean texture, mean parameter, mean area, mean smooth, explanatory variables, and this is the diagnosis, is the response variable. We want to see how these variables impact the diagnostics. So we are going to first run a model, a logistic model. I'm going to say library GLMnet. That's the library for a logistic regression. Then the next thing is to just name this fit. I'll call it fit 10, fit 12. I think fit 12. This is just naming. You can name whatever you want. Then I'll just run the GLM. That's the function for a logistic regression. I'll specify my data, my response variable, which is diagnosis, right? Then I'll specify my explanatory variables. I'm going to start with just for proper names. I'm just going to call the names of PC data, right? So these are the names that are in my variables, the column names. So I'll just copy them so that I write the actual names, right? Then you put a plus, mean texture, that's another variable, and mean parameter. Make sure to take the names as they are, don't put capital letters. Then mean area. Then the last one, mean smoothness. So these are variables, right? Then the next thing after specifying your variables is the family, to look at the family. So the family is going to be binomial because this is a binary regression classification. So binomial, then specify the link, which is going to be logit for logistic regression, logit. Then the next thing is to specify the data. The data is, like we said, BC breast cancer data, right? So this is, we have a challenge. It's fine, it's just a warning, it doesn't matter. Then we look at the summary. The summary is fit 12, right? So we are seeing we have an AIC of 181. So when evaluating a logistic regression, we mainly use this parameter AIC. So we want to see now if we are to add noise to this model, is the parameter going to change? Because the smaller this AIC, the better. So if we are to add noise, is it going to be small or is it going to increase? If it increases, it means the model is able to capture that this is noise. So let's create some randomness in the model. So I'm going to use set seed. I'm doing this just for reproducibility. If you want to also to run this, you get the same results if you put set seed. So what I'm going to do is I'm going to use R normal distribution. So it's called R norm. So how I do it, let me just give you an example. If you say R norm, then you specify your n to be, let's say 3. You are going to have 3 random numbers. These are just random numbers. And if I'm to use set seed and I say R norm, you see the numbers that I'm getting, they are the same as those ones. However, if I don't put set seed and just run this, I'm going to have different numbers. So that's why I'm saying let's use set seed so that we have the same numbers. Okay, so the next thing is to create these variables. I'm going to say BC data. That's my original data set, and I'm going to create a new variable called noise1. That's the new variable that I'm creating. And after creating this variable, how am I going to create it? I'm going to use rnorm to create some random variables, and I'll specify my n as the number of rows. N row means number of rows of my whole data set. So that means I'm going to have a column which is called noise1, and it is going to have random numbers, and those numbers, the number of rows for those numbers will be equal to the number of rows of the whole data set, right? So okay, we could just view this and see what I'm talking about. PC data. Right, so you see we have this new variable called noise1, and it has several random numbers, right? So that's fine. So we can create more of these, more noise, and this is gonna be 2. And I want to create 5. I think 5 will be fair. This is 3, this is 4, this is 5. So I have 5 random numbers, right? You can see we have 5 of these. The next thing now is let's now fit this model. I'm going to copy it, and this is the model where we are going to add some noise. So I'll do it step by step. I'll start with the noise1. The first, I'm gonna label it 13, then 13. Right, so let's see the AIC. It's now 182 from 181, so it's increasing. Let's create another one to compare. Probably it was just this one. Let's see if we add noise 2. Let's see what happens. This should be 14, and noise 2. Just copy it as it is. Right, let's run this. This should be 14. Right, it's now 183. It's increasing. Let's add another one. So we keep adding. We just want to see its capabilities. If I'm saying 15 here, and I add another one, it's gonna be noise 3. Right, it's now 184. It's rising. So the moment your AIC is rising, it means the model is getting poor. If I say noise 4, then this is 16. If I run this, 186, it's rising. Let's keep adding. Let's add the last one. So this is 17. Let's run this. Right, 188. So you see now, that's the advantage of using a more robust model like Logistic. It can capture the noise, and it actually increases the AIC to show that the model is becoming poor. We started off at 181, which was a good model, but it's now at 188, showing that there is no need for us to keep adding noise, and we can differentiate between noise and the actual variables. So that's it about this video. We wanted to show you how strong logistic regression is. We have done a video on linear regression, and we added noise to linear regression, and it performed so badly. It performed so good after adding the noise, which is a sign that it couldn't differentiate between noise and proper data, which is something that logistics did. So thank you so much. The next video we are going to talk about lasso logistic regression. We also want to see how lasso regression is also going to perform in face of noise, and which variables is it suggesting that they influence the diagnosis. So thank you so much.